So today I will be discussing contrasts, specifically their application in one-way and two-way ANOVA analysis, in addition to a brief discussion of orthogonal polynomial contrasts. So before we dive into what a contrast is and why we use it, I'd like to set us up with a lung volume example from class that I'll be using for my analysis. So just as a refresher, we're trying to answer the question of what impact elevation has on a bird's lung volume. Treatment structure is one way at 5 levels, where we're looking at elevations between 1,000 and 5,000 feet with 1,000 foot increments, with the response variable being mean lung volume. Now, when we're performing an analysis of variance on the data, we're really only able to determine whether treatments have the same mean response or not. This is what we're looking at when we compare p-values to a predetermined alpha level, also known as a global F-test. ANOVA does not, however, tell us which specific treatment means differ and to what extent. So what do we do if the global F-test is significant in this case, and we'd like to perform some kind of post-hoc analysis? Well, one way is to use what we call a contrast in order to more effectively determine any distinguishing features within our data. At the most basic level, a contrast is a linear combination of two population means. Contrasts are formed by comparing at least two treatment means or treatment effects such that the coefficients add up to 0. So just for reference, a treatment effect is simply calculated by subtracting the overall mean from the treatment mean. But both treatment means and treatment effects can be used equivalently for the sake of this discussion. In this example, we'd like to figure out if lung volume is different for birds at elevations of 1,000 feet versus 4,000 feet. To set this up, we're going to use the term gamma to define the contrast. As you can see, the coefficients 1 and -1 add up to 0. Therefore, this is a valid contrast. The null and alternative hypothesis in this example is that gamma is equal to 0 or not equal to 0, respectively. This is what we call a pairwise comparison, where we compare one mean to another. To test for any significant difference in mean response, one can either calculate a t-test or an f-test statistic, along with the corresponding p-value by hand, or through a series of commands in JMP. For the sake of brevity, I'm just going to be discussing how to complete the analysis in JMP. So to do this, we hit the analyze, then fit y by x, whereby we're going to input the proper variables. After hitting run, you'll find the drop-down arrow to find compare means, and then you're going to hit all pairs 2-key HSD, which will give you various reports about the pairwise comparisons. The connecting letter report gives you a snapshot of which treatment level combinations have significantly different means. Levels that are not connected by the same letter are significantly different. If you want a more detailed breakdown of the differences, the ordered difference report will provide the estimated difference, confidence intervals, and p-value for each pairwise comparison. Now, contrasts are not just limited to one-way treatment structures, such as the example I gave earlier. We can also compare means in a factorial treatment structure. So instead of just comparing a main effect of a treatment to another, we can also look at any differences between interaction effects. The same rules apply, though, where the coefficients of the contrast must equal 0. So take a generic example where we're analyzing the impact of treatment 1 and a treatment 2 on some response variable. Here we can set up a contrast for any combination of mu's such as the ones that I listed above. So for the first one, where it says mu11 minus mu12, it's basically asking if there is any significant difference in response between the interaction of the first level of treatment 1 and the first level of treatment 2, and the interaction of the first level of treatment 1 and the second level of treatment 2. Any test for significance can be completed by hand or through JMP in a similar manner to that I discussed before. So the last topic I'll be discussing is a special type of contrast called an orthogonal polynomial contrast. These contrasts are used when we have equally spaced quantitative treatment groups with equal sample size, and we'd like to look at the response curve of the data. These are great because they allow us to partition the variation of the data in the sense that we can see how much of the variation is due to a linear trend versus a quadratic trend, cubic trend, et cetera, et cetera. Now, one of the defining characteristics of an orthogonal contrast is that the sum of the coefficients of the first contrast multiplied by the coefficients of the second contrast are equal to 0. Additionally, the highest degree of polynomial for a given number of treatments is equal to g minus 1. So let's say, for example, we're analyzing the effects of 5 different equally spaced levels of caffeine concentration on plant growth. Looking at the chart provided, we can see that there are 4 possible orthogonal contrasts. So G minus 1, 5 minus 1 is 4. As such, the highest degree of the polynomial will be 4, meaning that we'd be able to analyze the data for a linear, quadratic, cubic, and lastly, a quartic trend in the data. So I hope this clarifies any confusion you may have had regarding contrast. If there's one thing to take away from this, it's that a contrast is simply a way of comparing treatment means to one another. If you have any other questions, I'm happy to help, and I'd like to thank you.